My name is Tal Dvir. I'm from the Department of Biotechnology, Department of Material Science and Engineering, and the Center for Nanoscience and Nanotechnology at Tel Aviv University. In 2011, I opened my lab at Tel Aviv University. Before that, I was a postdoc with Bob Langer at MIT. So my lab is working on developing cutting-edge technologies to regenerate defected organs, and we're working on different tissues. Among them is the heart. Heart disease is still the #1 cause of death in the Western world, and myocardial infarction captures a significant fracture of this disease. It happens when a major blood vessel that nourishes the left ventricle is blocked, and as a consequence, blood, oxygen, and nutrients are deprived from the ventricle. The cells in this area are dying, and since cardiomyocytes cannot proliferate, and since we do not have enough stem cells in the heart, this whole area becomes fibrotic, becomes a scar tissue, cannot contract, cannot send pulses of blood to the rest of the body. And currently the only solution for the end-stage patient is heart transplantation. In cardiac tissue engineering, we can isolate cells from the patient or from other sources. We cultivate the cells in two-dimensional flask, and then we seed the cells in three-dimensional biomaterials, porous materials, degrading materials that will mimic the extracellular matrix. Once the tissue is organized, we can take it and transplant it back on the defected organ, in this case the heart. Here you can see a typical cardiac patch that we develop in our lab. You can see the patch is contracting nicely, generating a strong contraction force, and we can significantly improve heart function. If we want to avoid immune rejection of this cardiac patch, we develop a new technology that we can use the patient's own materials to engineer the biomaterial, to engineer the scaffold. Therefore, we can create an autologous cardiac patch that will not provoke immune response after transplantation. Another exciting technology is where we integrate gold nanowires and gold nanoparticles into the biomaterials, and the cells interact with each other through these wires, through the gold. Integrating nanoelectronics within cardiac patches allows us to monitor, regulate, and control the function of the engineered tissue once they are transplanted on the infected heart.